So yes, if you take your FIP or you take subject for structure analysis, okay. Today we look at internal forces, right? Internal forces. We'll look at structure members and a diagram. Uh, So previously we looked at general forces. For example, the question 2 in your test 1. Okay. So you learn about external forces, right? Free body diagram. Look at the ladder. So the forces in A, and this one will move to the right. So friction force will move to the left, and there is a normal force at B. Okay, and also there is a mass effect, which is W. This is what we learned before. All right, all these are called external force, including the reaction here, and the loading of the weight. Today we focus on internal forces, where we want to see what happened when we cut the object, when we slice the object, what happened inside there. Okay, why it's important we know the internal force? Because when you go deeper, or you take a higher level learning, it's important when it comes to designing devices, right? You want to improve the devices. You want to optimize the design. For example, you think that, oh, this structure, where is the weakness point, and you want to strengthen it. So you need to do structure analysis, or you do it from the internal forces. You apply this one. Nowadays, we have all this in the software. But before you use the software, it's important you know how the software generate the data. Okay. We will not go into cables, right? We will not go into cables. We only stop at normal structure analysis for internal. Right? If we have time, then we go into cable. If not, then we just continue. Okay. Now, when we do design, structure design, we know that internal structure, like what you see on the screen here, all these members, they are helping to take care of some of the load. Right? The load is distributed inside the bodies. How we do analysis for chapter 7, or when it comes to test 2, maybe question 2, you will be requested to use method of section to do analysis. So this diagram you've seen before in the previous chapter. You do you do analysis on the external forces, right? So previous chapter, what you learn, you convert this one into free body diagram, and you copy all the forces, P1, P2 with the angle. Then here you convert into reaction force, where this one will be, okay, will be like this, RA X R A Y reaction. And what else? Is there any moment? This point. Is there any moment? Can it turn? Cannot, right? So there's a moment. Moment at A point. Okay. So by now, you should be able to convert what you see on the screen to the one that I draw on the whiteboard. If you don't understand, then you better go and do revision. Huh? Here, how we solve all these things? We use equation of equilibrium. All the force equals 0. All the moment equals 0. It depends on which one, how many unknown you have. So that's why this one, all the force equals 0. You can split into x direction, y direction, z direction. Moment, you only can catch any point you want. It can be A point, it can be P1 point, it can be P2 point. Okay, so this depends on how many unknown you have. Okay, now today we want to look into internal point of B. Okay, we want to dissect. So when you cut B, you need to split the body out, and then like what you see on the screen here. And I'll start to explaining how to draw the arrow in the middle here. Okay. The left, right, I already explained on whiteboard. So for the B point, when you cut and split, for the B point, you will have a contact point because these 2 points have contact. So when you split, you draw the arrow always pointing out first. Okay, you assume every time you cut, you separate, there's the contact force always pointing out from the body. You assume first. You assume first. Then later you do analysis, you get negative, means it's wrong. What you draw in your fiber diagram is wrong. You need to flip the direction. You will get negative. Okay, so first force you draw on the split section is the contact force. So these two must be opposite direction so that it cancel the forces. Okay, so NB left hand side body plus NB right hand side body, it will cancel these forces. So no NB actually. After that, because these are joined, it cannot go up, go down. It cannot go left, right. So you will have NB, and also there is a shear force, right? Or go down force. So one go down, one go up. The arrow of left hand side, why go down? Because you want to balance the AY force. Yeah. So I just slow down a bit. You already have external forces. So first, there is a contact force pointing each other, and it must go out. The arrow must be pointing out. Then the forces xy, so this one, let's say you draw AY go up, so there's a force balance the AY, so there will be VB, or you can say BY if you want, because it's a B point. BY, just to represent this on the left hand side, so you just maybe you label something this one. So on the right hand side, because you have this VB go down, it must balance the VB. So another side, you just flip the direction. So this one will cancel this one. Okay. So everything what you see on the left and right will be opposite direction. It just balance anything. Then if this one cannot twist, if this one cannot move in the rotation direction, then there will be a moment. Okay. So how to determine the direction? If your A is clockwise, so this one, when this body already turned like this, so this point will turn like this. This blue arrow will follow the point A. Because if you cut and then you turn this one, this will follow this direction. And you need to cancel this one. So you copy this arrow, flip the arrow, it will become clockwise direction. Okay. You don't touch the external force. You don't touch the external force. So for chapter 7, when question asks you to do internal loading analysis, you need to solve the chapter 1, 2, 3, 4, 5, 6 analysis. You solve the external forces. Then only you come into internal force. Then only you cut according to the question you ask you to do dissect on the section B. Then only you split and you copy whatever value that you solve to the two diagram. Make sense? Any question? Okay. So in your answer, it's not necessary you write VB, not necessary. Why VB? Because if you learn about shear force means the force go parallel with the surface. It's called shear force. And in engineering, we usually will use V to represent shear force. But you use other notation also okay lah for this subject. Okay. So the rest you read, I already explained. All right. Moment means you see things inside there is called bending moment. You bend the thing. All right. So later you need to convert all this arrow into diagram, into graph. Okay. When you cut the object in the middle, you will have shear loading. You will have bending moment. You have two things inside the bodies. Again, why is shear? Because the force is parallel to the area, the cutting area. Why there's a bending moment? Because of the twisting, you can bend the steel. Okay. Okay. So why the opposite direction? Because you want to balance the force, and also we follow the Newton third law. The thing, if it continue to stay, it will continue to stay. If it continue to move, it will continue to move. Or reaction is opposite of each other direction. Okay, then the rest. Equation of equilibrium, you solve external force. How you find the value of VB, NB, and MB? Same. Just now you look at overall system. When you draw the section, you pick one section and then you solve with equation of equilibrium for that component. Means this one set, all the force equals 0, all the moment equals 0. For the left segment, you solve. If you still have unknown, don't worry. You go to the another component, use all the force equals 0, all the moment equals 0, solve for this one. Then you compare left, right. There are some components that you can solve simultaneously. Okay. If you understand this one, basically you already 50% understand about chapter 7. 50%. Means this chapter you already know what to do already. Okay. The another half is diagram. Another half is diagram. Okay. Okay. Now what about three-dimensional? Just now is 2D, right? Just now is 2D. 3D also same. You will have all these parameter. So you have normal force, which is normal to the surface. So N, Y direction, X direction, Y direction. So the normal force is because the force is perpendicular to the surface. V because of the force go parallel to the surface. So if you don't want to confuse between normal force or shear force, you just use a capital letter just to represent the force on the surface. Okay. And then each axis have its own moment. We call it torsion moment or bending moment. Right? Torsion. You can twist in X direction, Y direction, Z direction. This is for the three-dimensional component. Okay. This is just a rules or general rules we use when we do internal loading analysis. So if you have the structure pulling both ends, we call it tensile loading. pulling both ends. You're pulling it. So pulling it, when you cut the center, you just imagine the object, the middle part, they want to seal together. They want to join together. So want to join together, the force will always pointing to each other. This is when you have tensile loading. Okay. What happens if you have compressed force? You compress, the two things will try to push each other. Okay. The logic will be that lah. Okay. So another one is shear loading. So you just, when you cut, shear means you turn the thing lah. You cut the thing or things. So you cut in the middle. You just copy the arrow, flip the arrow in the middle. Okay. Left hand side, if you cut in the middle, this one will flip this arrow, and then right hand side also will flip the arrow. Okay. Okay. And then moment. Also same. These are the traditional positive direction. So positive, you get positive, or when you before you start, you look at the object. When the object is having tensile loading, then you have positive normal forces. Means you're always pulling out positive. This is a positive shear. With this left hand side go up, right hand side go down. Okay. So left hand side go up, right hand side go down. This is called positive shear. This one, positive moment. Positive moment. How you remember positive moment? When you bend this object, left, right. What shape you see? Smiling face. When you bend this object, you see a smiling face. Smiling face represent positive moment. When you bend the object and the object have a smiling face, remember that is a positive moment. So if the question mentioned the object subject to positive moment, then when you draw free body diagram, remember to draw moment direction in this way. Okay, then when you cut, you just flip the direction, flip the direction. Okay. Okay, this is just for your reading, how we solve the internal loading, this one. Basically, you already know lah. It's just that it's just for your test revision notes lah. Okay. Okay. Let's try to solve this question. Determine normal force, shear force, bending moment acting just to the left, point B, and just to the right, point C, of 6 kilonewton force on the beam in the figure. So this one, when you look at this diagram, can you do external force? Again, free body diagram, don't give me one dot or one line. You need to draw the body. Okay? The name already give you free body diagram, so they should have a body. Label A, label B, and then copy 6 kilonewton forces, put in the dimension 3 meter, 6 meter. What is the force at point A? What is the reaction force? You only have one, AY. Can it bend? Can it rotate? Yes, because it's a pin and it's a round this one. So it can rotate. So no moment. For point D, it cannot move left, right, but it can rotate because there's a pin. So you have By and Bx. Again, this arrow is, we assume. And there's one external moment there, 9 kilonewton moment. So you just copy. The question asks you to analyze the forces just a little bit to the left of 6 kilonewton. Okay, so we start with the point. just a little bit to the left. So when you cut point B, what do you see? You copy. This is point B. I cannot say. This is T. This is T. This is T. Okay, this is point B. So you just copy external force. How you draw B? Okay. Contact force. B. What else? Shear force go down. Y go down. Y go down. It should be go down. Okay, it's my opposite of this one. VB. What else? Moment. In this case, we just assume lah. So this one rotate like this. So it will rotate like this. If you rotate, it will. This one also rotate like this. So rotate. This one will rotate like that. So we just assume lah. We just assume it go this way. MB. Assume this one assume. Okay. So okay. So again, how to solve AY and AD? This one again, all the force equals 0, all the moment at A point or D point equals 0. You're able to find AY and AD. This one you split into X and Y. In this case, you know that this Y, because it's Y direction, so you just need to do all the force in Y equals 0. You don't need to do X. Of course, you need to solve AX. In this case, you know your AX 0, DX 0. No X direction. Okay. Okay. I'll just give you the answer. You copy everything and you put in the green color arrow. Okay. Dx, dy, there's a moment, 9 kilonewton meter. Okay, so you should be able to solve unknown. Dx will be 0. You cannot straight away write dx 0. You need to write all the force in x 0. Then from free body diagram, this one is from free body diagram. So in free body diagram, you only have one dx equals 0. Then only you get full mark. If you straight away write dx 0, I'll put question mark. How? If you only straight away write this, I will write how. You won't get marks. This one? How you find AY? By taking moment at D equal 0. When you take moment at 0, D at 0, dx, dy effect gone, but you have an external force. Remember to copy this external force in your answer. So, and also every time when you do something, remember to give direction of your calculation. We assume anti-clockwise positive. So if you have a moment in D equals 0, AY will give you positive or negative value. AY will give clockwise or anti-clockwise direction. Clockwise. So clockwise will be negative. Multiply by distance of 9 meter. So in your calculation, you can skip the unit, but the final answer, please give unit. So then plus 9. This one kilonewton. Kilonewton. That's right. So this one is 9 meter. So your AY is kilonewton. Equals 0. So you should able to see your AY already lah. AY is 1 kilonewton. Okay, once you find your AY, back to, you can either use moment at A equals 0 again. Okay, anti-clockwise positive, or you can go back to all the force in in Y equals 0. Go up positive. Then you balance all the Y. Yes. Huh? 6, this one. Oh, yes, there is a 6. So moment D, there was a 6. So 6 will be positive 6 plus 6 kilonewton 6. Okay. Like that lah. So important, you know what is the step you need. Remember to use the equation of equilibrium to solve. Okay. So you get AY. So the rest is solved lah. But important is still back to example 1. The question asks you to analyze the forces just to the left of 6 kilonewton. So you draw the point. The 6 kilonewton was not seen on the left-hand side B, on the B point. So don't draw that. So here you have a few point there. So you just draw lah. So then you solve lah. Okay, you solve. You manage to find NB equals 0, because if you look at this diagram, this set is for segment AB. So in your answer solution, please write this statement. What segment you do analysis? So I know what you do. Then write the equation. Write the equation. I just keep the things. So NB, no x direction, 0. Y, you have AY, VB. So you already find your AY. Substitute there, you find your VB. Moment, we do at B. Then you can find your MB. Okay. So once you solve this one, you do for segment C. Same. Segment C, you already start to see 6 kilonewton. You cut C there. Wait, segment C. No, segment C also didn't see the 6. You miss out the 6. Okay. 6 is on the left-hand side of C, so it didn't. The focus load was not pointing to the C, so no 6. Same solving equation using equilibrium equation. You can find the missing parameter on the free body diagram. Okay. Any question? Any question? No, easy, right? The rest you read lah. Okay. Now I think more challenging part is you see the distributed load lah. Okay. I already explained there's an appendix to check, right? Okay. So every time you see a triangular distributed load, important is always 1/3 of from the base. That point, all right? So you convert, determine the normal force, shear force bending at point C for the beam in the figure. So when you see distributed load, the first thing is to convert this distributed load into focus load, and then determine the location of the focus load. Convert this distributed load into focus load before you solve anything. Okay, this is the first part. Second part, then only you do the external forces, external analysis. This one was mounted to the wall, so you have X, Y, and moment. Okay, label carefully. And then the focus load will be 1/4 from the wall, not quite 1/4, 1/3 from the wall. So the total length is 3. The total length is 3. So 1/3 is 1 meter from here. The focus load will be here, 1 meter. Okay. Then the rest is just depending on the question asks you where is the internal force that you need to analyze. So I just show you the steps. Okay. First, you just convert the distributed load into focus load, right? So this step, what trying to do is, because point C is at the middle of the part. So you want to see what is the distributed load at point C. You want to find how many Newton over meter at point C. So you use a scale triangular. You use this scale triangular. So this 1,200 Newton meter at the distance 3 meter from the tip. And this X value or WC value is 1.3 meter from the tip. You do ratio. This one divided by this one divided by this one, and you move around. You'll get WC equal to 600. So at this point is 600 Newton over meter. Okay. Once you find WC, then you cut the section. You put in the thing. So when you cut, you just copy the WC value and copy the triangular. Triangular. You copy that. WC already calculate. And the length of section is 1.5 meter. And 1.5 meter, you know that you're still seeing triangular. So this is a distributed load, is always 1/3 distance from the base. So I'll just give you the appendix there. This is from the appendix. The location of the distributed load, 1/3 from H, this one, 1/3 of B, of B base. The height of the location of the height is 1/3 also, okay, from the base. So if you continue the calculation, you put in all the value, convert the triangular distributed load into focus load. Okay, how to convert focus load? It's a triangular, it's area inside the triangular. So area of triangular is half base and height. And remember, when you cut something, there is a connecting force or pulling force. So it's pointing to the left, normal force NC, and there's a shear force also. Okay, shear force should be pointing up or down? Up, because you need to balance the WC component. Okay, then there's a moment. There's a bending moment. Bending moment, in this case, we assume it will follow the motion of this component, because when you press, you would try to rotate this object. Okay, so we assume it's in this direction. But again, if you assume wrongly, you draw an clockwise direction, also okay. It's just that later you do equation of equilibrium, the moment part, you will see that you get negative value. Okay. Okay, so in this case, we purposely put MC clockwise to show what happened in your calculation. Okay. So just a reminder here, always follow anti-clockwise in your solution at the standard step. So if you don't know, you just put moment or anti-clockwise. Okay, equation of equilibrium, you use these three equations. You look at segment CB, all the x equals 0, so your NC equal 0. Okay, y, you solve all the y. So VC go up positive, and the red arrow half 600, 1.5 is go down, so negative. So this usually will be the careless mistakes. So here you can solve your VC. Then moment. Moment, again, we have, in this case, we put clockwise positive. Clockwise positive, so 0. NC will be, this one is anti-clockwise, so negative. So this one at C point, uh, at C point, here. At C point, you will see this one. This one multiplied by 0.5, you get moment. So this one is clockwise direction, so you get negative. When you solve, you get your MC is a negative value. So when you get negative value, it means what you draw in your free body diagram actually is wrong. You need to flip the direction. Okay. Or if you want to maintain your free body diagram, also okay. If you draw like this, then your answer is negative. You don't change your free body diagram. I also accept one. Okay. So, but however, if you already draw the purple color arrow anti-clockwise, but your answer is negative, then it's wrong. What you do is wrong. Okay. So you must agree with the scenario lah. So what I recommend always is after you draw, after you first attempt, you get negative. If can, you redraw the free body diagram. Then change this one to positive. Okay. But if you want to stay answer like this also, okay. But you must remember the correct direction of MC will be anti-clockwise. Okay. Or in some case, I will just recommend you after you get negative, MC equal to negative 2 to 5 Newton meter, you can write or MC equal to 2 to 5 Newton meter give direction. This one should be it should be anti-clockwise. Okay, Alisa. Any question? Yeah. Mm. No need, no need, no need. So if you arrive at this answer, you can stay at this one. You just need to add on this statement or MC equal to 2 to 5. Just convert the exact direction of the moment. Okay, yeah. So this one is your homework, but I'll go very fast. Just observe the steps. Just observe the steps. How we solve this one. So we look at the question. He asks you to solve normal force, shear force, bending moment acting at point B, which is here, of the two-member frame shown here. So before you solve the question, you need to convert the distributed load into focus load. And that is your task lah. Okay. Then after that, you solve external reaction force. The focus is asked you on this member. So when you focus on this member, convert this reaction, this connector here into forces. This one also. This one is This one you assume the force will be, if this one press down, what is a C point feel? You will feel the force pressing in or pulling out. Press, right? If your C point, you'll see this one poking inside. So the force will be like this for C lah. Okay. You observe how the solution. You copy the object, copy all the dimension. Okay. Then you break. If you really don't know, you break the component out first. You put in all the component. Okay. A point, the moment is 0 because there's a pin there. Point A, there's a pin, so pin able to rotate the object, so no moment. Okay. So if you really don't know, you just break these two into component. Then you imagine this one press down. What feel by this object? This one will be compressed. So compressed, they are load in this way and load in this way. Then you flip this force to another side, pointing to C. Okay. Okay. So you just do calculation, the length of this one. Sometimes you can simplify the triangular. Okay. Once you have that, solve for reaction forces, external force. Okay, you see that the distributed load already converted into 1.8 kilonewton. This whole section of 750 Newton per meter already converted into 1.8 kilonewton. Okay. Who don't know how to calculate 1.8 kilonewton? Who don't understand how to get 1.8? Who don't know how to convert this 750 into 1.8? Okay, then you solve. You still using the all the force equals 0, all the moment equals 0. Okay. Again, the moment point is free to choose. You can choose B, you can choose A, you can choose C. Okay. Once you do that, you have solved all the external forces already. You solve all the external force first, then only you go and do internal force. Yes. This one? 1.5 is huh? It should be 1.8, I think. Wait. 1 point. DC, right? FDC issue. Uh, check this one. It is what 1.5 or what 15. Sometime typo error in my slides. If you press calculator, can you help me to find FDC whether it's 1.5 kilonewton or 15? I think it's 1.5. Can you help me to check this mathematics? 1.8, 1.2. How many? What's the FDC? Is it 1.5 or 15 kilonewton? I don't think it's 15. Is something missing in my calculation? Okay, check. Uh, okay. So let's try to solve this one. You split. Yeah, we spend a minute just to prove this question. Sometimes my slides, I put in the wrong value. Okay. AX, AY, you have 1.8 kilonewton. You have FVC. So the angle theta, so we have a triangular for, huh? This one, right? This one, there's a distance. Um,
Moments about P, the reference point is actually A.
this one, it should multiply 1.2. If you took a B, you look at FDC, it should be 1.2.
I think the paper is supposed to be more.
Oh, it should be C. It should be A point, or I think it should be A point, not B. Okay, this one should be A point. Okay. Okay, so let's just try to solve this one. 4, 5, 3. So this one is FDC. all the moment in A, 0. Anticlockwise positive. So 1.8, 1.2, plus negative FTC over 5, 2.40. TC I get 1.125, or okay, it should be 3 over 5. Okay, this is 1.5. So typo error in my slides. FTC is 1.5 kilonewton. Then the rest you just do all the x equals 0, all the y equals 0. Okay, typo error on my slides. Again, be careful in your assignment. This question might come out in your assignment. If you copy this one, you don't get the full marks for assignment. Okay, the rest you read the rest of the example. As you can see, the diagram split into two halves, AB and BC. You still need to copy the distributed load. You still need to copy the distributed load 750, and then this is a rectangular. So at the half of the distance, this also half the distance. Okay, go home, see this example. Example 4, also go and see. Example 4, very high chance will come in your test too. Go and see. Example 4, example 5. Okay, so we have done the first part. Next lecture, we look at beam. Beam is important for civil engineering. Your attendance, you're here.